Point we have talked about electrons. We know the nucleus is in the center of an atom, and electrons all hang out. And over the last couple of days, we learned that they not only live in energy levels, but they live in sublevels, and then lastly, they live in orbitals, correct? So today we're actually going to give the specific location of electrons. We're going to give what I like to call their address. We're going to learn how to write an address for each element. So electrons in the nucleus interact to make the most stable arrangement possible. So elements want to be stable. Elements want to be unreactive. Elements want to stay all by themselves. So they try to arrange their electrons to create this idea of being stable. They're not all necessarily going to be stable, but they try to get as stable as they can humanly be. So this leads us to something called an electron configuration. This is the way electrons are arranged in various orbitals around the nucleus. So this is how we can write it. This is how we can communicate. This is how we can do all of this information. Okay, so in order to do electron configurations, we actually have to follow a set of rules, and this is hopefully going to glue all of this information together. So the first rule that we're going to talk about is called the off-bow principle. Some of these have interesting names, and the reason they have interesting names is because they are named after the scientists who discovered them or came up with the rule. So the off-bow principle says electrons occupy the orbitals of lowest energy first. Remember yesterday when we were using our periodic tables, didn't we put electrons in 4s before 3d? Red flag, that didn't make sense. Why does it do that, Miss Tackett? Why? Well, this rule says that we have to put them in the order of lowest energy, not lowest quantum number. Okay, so this is actually another way to look at... Okay, some of you like using the periodic table. Some of you will come to love that, but this is actually what I was taught to use using this principle, was this diagram. And it looks kind of hard to make, but it's really not. So to make it, you just start with 1. In the first energy level, we have 1 sublevel. In the second energy level, we have 2. In the third, we have 3. In the fourth, we have 4. And the fifth kind of mirrors it, correct? Yeah. So it's going to do 5s, 5p, 5d, 5f. Then the 6 starts to go back down. So then it's 6s, 6p, 6d, and then 7s, 7p. So it's like a pyramid that mirrors itself, correct? So then how we read it, just like in the periodic table, when I was asking you to list the order of the sublevels, didn't you read from left to right? Same thing, except this time we're going to draw arrows. So I put electrons in the 1s sublevel first, followed by 2s, followed by 2p, and then 3s. Then I go up here to 3p, 4s. Then I do 3d, 4p, 5s, 4p, 4t, 5p, 6s, 4f, 5d, 6p, 7s. Wow, it really starts to get out of order, huh? Then we do 5p, 6d, 7p, and we're done. So, probably 80% of my students like the periodic table way. 20% of them, the periodic table makes no sense, and they like this diagram. It doesn't really matter which way. It gives you the same information, doesn't it? One's just easier to memorize for the other one, depending on who you are. So I just wanted to show you the second way. Some of it makes sense, some of it doesn't. Okay, so now let's move on to the second rule. The second rule is the Pauli exclusion principle. This principle says that a maximum of 2 electrons can be in any orbital, no more than 2. You can have less, you can have 1, you can have none, but you can't have more than 2. And not only does it say that, it also says that electrons have to have opposite spins. Well, if you think about it, aren't electrons negatively charged? Shouldn't they repel each other? Shouldn't they push each other away? So if they're pushing each other away, how do they occupy the same space at the same time? They have to have opposite spins. It doesn't really fix the problem, it just kind of puts a band-aid on it. So That moves us on to, well, they're in two per orbital. They have opposite spins, so how do we represent that? We represent that by drawing arrows. We don't know, we can't see electrons, we don't know what they look like, so we have to draw arrows. So if you look down here at the bottom, this is actually called an orbital diagram. It's an orbital diagram with an element that has 5 electrons. It's showing you that these 5 electrons are in 3 various orbitals, but we draw arrows to represent the electrons, and if you notice, I'm drawing them in opposite directions to show you that they have opposite spins. So one is spinning upwards, one is spinning down. Spinning up, one is spinning down. Okay? Number of electrons. The arrows are representing electrons. The boxes are representing orbitals. But we're going to learn how to draw that in 2 seconds. Okay, the third rule, you guys ready? Okay, the third rule is called Hund's rule. Hund's rule says each orbital within a sublevel, so some sublevels contain more than one orbital, correct? Does 1s contain more than one orbital? No, any sublevel with the s only has 1, but p sublevels have 3, right? So any sublevel that contains more than one orbital, we have to put electrons in one orbital, each orbital, before we can go back and pair them. So for instance, if you look at the orbital diagram for nitrogen, we see 1s only has 1 orbital, so we drew 1 box. 2s has 1 orbital, so we drew 1 box, but 2p, p has 3 orbitals, correct? So we drew 1, 2, 3 boxes to represent the different orbitals, but if you notice, you have to put 1 electron in each box before we went back and paired them. Well, nitrogen has 7 electrons, so if we count the arrows, we're going to have 1, 2, 3, 4, 5, 6, 7. So we have 7 electrons, but we had to put 1 in each orbital before we paired them. So where do you think I would put an 8th electron?
In the 3rd box.
In this box, correct? Where would I put the 9th one?
Next box, going down.
And what about the next one? All right, so let's practice drawing an orbital diagram. Let's see if we can draw an orbital diagram for oxygen. Okay, first of all, let's look at oxygen. Oxygen has how many electrons?
8.
8 electrons. So I'm going to just make a note of that so we don't forget. And we are going to write the orbital diagram for oxygen. So, first of all, we always start with what sublevel? 1s. How many orbitals does it have?
1.
So how many boxes am I going to draw?
1.
After 1s, where do we go?
2s.
2s. How many orbitals?
1.
So how many boxes?
1.
After 2s, where do we go?
2p.
2p. How many orbitals does 2p have, though? 3. So I'm going to draw 3 boxes. Say, how do I know to stop at 2p? Oxygen is located in 2p on our periodic table, right? So now I have to go through and I need to plug in my electrons, my 8 electrons using the rules. I have to fill in the lowest energy levels first. I have to put 2 in each orbital, and I have to fill 1 before I go back and pair them, right? So we go 1, 2, 3, 4, 5, 6, 7, 8. This is the orbital diagram for oxygen. How many empty orbitals do we have? None. How many half-filled orbitals do I have?
2.
And how many full do I have? 3. This is important because when we get to bonding, which will be in the next couple of units, this right here is what makes oxygen bond the way it does. These half-filled orbitals or these empty orbitals is what makes atoms bond the way they do. All right. So we just drew the one for oxygen. Which one was the correct answer?
B.
B. B was the correct answer. It has 8 electrons following the rules. So let's look at the other ones. Why is A wrong?
Because it doesn't have this is empty orbital.
Right here, we know that the Hund's rule, the third rule, says we have to put 1 in each orbital before we go back and pair them. There's things paired, so that's wrong, correct? What about C? Where is C wrong?
One of the other ones is not full.
This one is not full. We couldn't move to 2p until 2s is full, correct?
Yeah.
And then what about D? Not only did we not fill 2s, but we left it completely empty. So this one is also not following the fill the lowest energy level before you move on to the next one, right? All right, well, I don't know about you guys, but drawing boxes and arrows really isn't all that much fun. So there's actually a shorthand to do this. This is what I like to call writing the address to an element. When you guys write an address, you put N for North, you put MO for Missouri, right? You have shorthand ways of writing things because you don't want to write everything out. Same thing here. So when we are writing the electron configuration, we write the number of the energy level. We then write the type of the orbital, so kind of like the sublevel, right? And then all we do is we add the number of electrons as a superscript. So I'm going to draw one out for you. I'm actually going to put oxygen back up here in just a second. So let's look back at oxygen. Really quick, I'm going to throw the orbital diagram up really quick. So oxygen, oops, backwards. You remember what oxygen looked like? Oxygen looked like and sometimes this is another way of writing orbital diagrams. You don't actually have to draw the boxes. You can just draw lines and put arrows on top of them. So this is what oxygen looked like, correct? This is the one we just drew 2 seconds ago. Okay, this time around, I don't want to draw boxes and or lines. I don't want to draw arrows. I don't want to do the spins. We're just going to do the electron configuration. Well, to do the electron configurations, you just start with your sublevels. So 1s, and how many electrons are in 1s? 2. So you write 1s, 2. Next sublevel was 2s. How many electrons? 2s, 2. Next sublevel is how many electrons? 4. So 2p, 4. This, your electron configuration, and your orbital diagram are giving you the same information, correct? The only difference between the two is your orbital diagram shows you the orbit. So if I'm asking you questions about orbitals, how many are half filled, how many are empty, so on and so forth, it's a lot easier to answer those questions if you have the orbital diagram. But it's a whole lot easier to write your electron configurations, right? Okay, so I want to do a blank one. So let's look at chromium. So somebody look up chromium for me. Tell me how many electrons chromium has. Chromium has 24 electrons. So let's do a practice. Let's do the orbital diagram and the electron configuration for chromium. So what is the first sublevel we start with? 1s. How many orbitals? And I'm just going to draw lines. I don't draw very pretty boxes. After 1s we do? How many orbitals?
1,
After 2s?
2,
How many orbitals?
3,
What's after 2p? How many orbitals? 1. After 3s we're going to do 3p. How many orbitals? 1, 2, 3. After 3p? 4s. How many orbitals? And after 4s? 3d. How many orbitals?
5.
1, 2, 3, 4, 5. Okay, so now I need to go back through and I need to be adding my electrons, right? Following the rules. So 1, 2, 3, 4, 5, 6. Actually, it was 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. How did I know to stop there? I have no more electrons. So, how many empty orbitals do we have? One. How many half filled? And then how many filled? 10. So again, this information over here, the half filled and the empty orbitals, is what's going to make it bond. Now, let's see if we can write the electron configuration now. You start with 1s, correct? So you do 1s. How many electrons are in 1s? Then you move on to what? 2s, how many? Then 2p. How many? 6. After that you do? How many? Then 6. Then what? 2. And then 3D. 3D 4. And I'm running out of room, so I'll put it on here. Why do I have 4 boxes on 3D? I don't. I have 5. 2p. I don't. This is 3s.
Oh, I didn't see it.
Okay, so do you have to draw an orbital diagram to do the electron configuration? No. Would you guys like to know how I do it? What I do is I get my periodic table. I put my finger on whatever element I am talking about. So like we just did chromium, so I put my finger on chromium like you see here. So I know that every sublevel before 3D, because I'm in 3D, correct? Every sublevel before that is full. So I don't even have to look at the periodic table. 1s, well, s can hold 2 electrons, so it must be 1s2. 2s, well, 2s can hold 2, so it has to be 2s2. 2p, p can hold 6, so it must be 2p6. I know that they're all full until I get to 3D, so I just sit there and write until I write down 3D. Then when I get to 3D, I count starting at the first one, which is SC. I go 1, 2, 3, 4. So I know my last thing I'm going to write is going to be 3D4. So that's how I do it. You don't have to write the orbital diagrams. You don't have to do something fancy. I just know that you look at the sublevel you're in, everything before that is going to be full. Okay, one more thing I want to talk about before I erase this is exceptions to the rule. There are people that do not follow the rules. Chromium is one of those examples that does not follow the rules. So let's look at chromium's last couple of sublevels. I'm going to draw them a little bit bigger for you. So chromium has its 4s, and then it has 3d. Not all elements follow the rules because if you remember, the whole point of doing an electron configuration is for you to create the most stable form possible, correct? So, sometimes the most stable form is not the correct form. Sometimes the most stable form is not following the rules. I don't expect you to be able to tell me when somebody doesn't follow the rules. I don't expect for you to draw the correct orbital and or electron configurations, but I do expect for you to understand why some people don't follow the rules. So chromium does not follow the rules because it is more stable to break the rules. Which rule is he going to break? He is going to break the off-bow principle. Well, if you look, he has one lonely orbital, right? Nobody's over here in this orbital. Well, he says, I have 2 guys in 4s, but I have 0 guys in one of my 3D orbitals. So what he does is he takes this electron and he relocates it over here. And to him, it is more stable to have 6 half-filled orbitals than to have 4 half-filled and 1 empty and 1 full. To him, it's kind of like a balancing beam. It is more stable for him to put 1 electron on each than to have some full, some half full, some empty. So, why does he not follow the off-bow principle? He's trying to become more balanced, which will yield for him to have a more stable electron configuration, right? So again, do I expect you to be able to recognize this? No, but I do expect for you to be able to explain why, and it is a test question. Okay, so if you guys don't like that explanation, you are more than welcome. The book does talk about it more specifically. It actually gives you lots of examples. So if you want to look on page 135 and page 136 to kind of read through the examples, you don't have to do 8 and 9. But if you want to read through those few examples to kind of maybe help it solidify you for the test a little bit better, go for it. But for today, what I would like for you to do is I want you to work on some homework questions. Okay, there's only 7 of them. They ask you to look at some orbital diagrams. What rules are being broken? They ask you to decide what element is being represented. It asks you to draw orbital diagrams. It asks you to write electron configurations. The only way we can learn how to do this stuff is if we practice. So you have 12, 13 minutes to do this. You really shouldn't have homework as long as you're doing your homework, okay?